Dear learners, welcome again in crystal structure lecture number 7 for B.Sc Physics TY students, paper number 13A, solid state physics. You are welcome again in Sanjeevanee Mahavidyalaya, Chapoli, Department of Physics. Now let's discuss simple crystal structure. There are various types of structures depending upon the nature of the atoms arranged in it. In the interior of the crystal, how atoms are arranged. So depending upon the positions of the atoms, crystals are again of different types. Now let's turn towards first one, FCC, that is face centered cubic crystal structure. What is FCC? Long form easily you can remember, face centered cubic structure. But what is meant by FCC? How FCC structure is physically going to appear? These things we are now going to study. Here you see, in case of FCC, atoms are arranged at the corners and center of each cube face of the cell. What I am telling? Atoms are arranged at the corners. I will show you figures so that you will get idea. See how atoms are arranged at the corners. 1, 2, 3, 4, 5, 6, 7, 8 corners atoms are arranged. These atoms are not only arranged at the corners, but they are arranged at the centers of each face. Suppose this is right side face, here atom is arranged. Upper side face, here atom center. Left side face, atom is arranged at the center. Here bottom side face, arranged here. Front side this, back side this. I mean, the atoms are arranged at the corners and at the centers of the face. So like this. Now in this way, atoms are arranged at the corners and center of each cube face of the cell. This is nothing but FCC, face centered. Name itself says that it is a face centered cubic structure. With the help of these two figures, you might have got an idea of FCC, face centered. If we think about its closed packet plane, on each face of the cube, atoms are assumed to touch along the face diagonals. 4 atoms in one unit cell, and the edge is to be obtained by using the relation 2r under root 2. Using this formula, we have to solve again some problems. We are going to discuss problems again. Now let us turn to the next one, body centered cubic structure. In short, it is said to be BCC, body centered cubic structure. Now what is body centered cubic center? In case of body centered cubic structure, again atoms are arranged at the corners of the cube with another atom at the cube center. What? With another atom with the cube center. See here, I will show you figure. Here atoms are arranged at the corner, and one atom is arranged at the center of the cube, remember, not on each face like previous case. It is arranged at the center. You see here, search center here. An atom is arranged at the center. This is the difference between FCC and BCC. In case of FCC, what we have seen here, atoms are arranged at the corners, no doubt, but atom is arranged at each face at the center. Now here you see figure is different. How it is different from this figure? Here atom is arranged at the center of the cube. Center of the cube, and in previous case it is at the center of the face of the cube. Here center of the cube. No doubt atoms are arranged at the corners. This, and this. And one more atom is arranged where? It is at the center of the cube. So this you remember carefully. Now closed packed plane cuts the unit cube in half diagonally. Two atoms in one unit cell are there, and its length can be calculated by using 4r by root 3 relation. This relation is also useful while solving the problems. We are going to discuss problems also, so that you remember this formula. Now next one is hexagonal closest packed structure. We say HCP. Now what is hexagonal closest packed crystal? Shell of an hexagonal closest packed crystal lattice is visualized at the top and bottom plane of 7 atoms. How many atoms? 7 atoms. When we see figure, then you will come to know. 7 atoms forming a regular hexagon around a central atom. Hexagon, you know, there are 6 sides. It is a closed figure having 6 edges, and each edge is of equal length. You know, hexagon. So top surface and bottom plane become what? A regular hexagon. 7 atoms are there, forming regular hexagon around a central atom. In between these planes, there is a half hexagon of 3 atoms. There is half hexagon of 3 atoms. Now we see figure, so that you will come to know. See, there is a center one atom. This is upper face, and this is bottom face. Top, bottom. Here in this figure, again, if we count these sides, 1, 2, 3, 4, 5, and this one is 6. Here each side is equal in length, each edge is equal in length. So this we say it is a hexagon. But we can say that it is a hexagon, not only hexagon, but it is a regular hexagon. And here regular hexagon of 6 atoms, and 1 atom is at the center of the regular hexagon, not only at the top surface but also at the bottom regular hexagon. And one more thing, already I have told you, there is a half regular hexagon in the interior of the crystal. So here you see this figure. There are 2 lattice parameters in HCP. What are those? A and C, edge and height. Actually all the edges are equal, but height is not equal to the edge. You are getting it? So we say there are 2 parameters in HCP, A and C, I shown in figure, A and C, representing the basal and height parameters respectively. A represent the basal parameter, and C represents what? Height parameter. There are 6 atoms per unit cell. You can observe carefully and then you remember. Now we discuss coordination number. What is coordination number? The number of nearest neighbor atoms or ions surrounding an atom or ion. Coordination number is nothing but the number of nearest neighbor atoms or ions surrounding an atom. For FCC, I mean face-centered cubic crystal, hexagonal cubic HCP systems, the coordination number is 12, and for BCC body centered, the coordination number is 8. Remember, for FCC and HCP it is 12, and for BCC it is 8. Now let's turn towards atomic packing factor. Atomic packing factor is nothing but the ratio of atomic sphere volume to unit shell volume, assuming a hard sphere model. And in case of FCC and HCP, this packing factor is 74%, 26% void space in unit cell. Void space in the sense what? The space between this, I will show you figure. Sir, here you see here space is showing here. White color space is there in between these atoms. This is said to be what? Void space. So from this figure it is clear that what is void space. So here it is given void space is how many percent? How much percent? 26% void space in unit cell, and BCC 68% atomic power factor is given to us. Now there are two problems. Here in case of PB lead, 0.75 nanometer is the radius, and we have asked to find out the unit cell, volume of the unit cell. With the help of radius, we can obtain first of all length of the edge. It is 0.495 nanometer. Volume of the cube, you know, side cube, it's by putting the value, we obtain this value. In this way, problems may be asked in examination. Second problem is in case of magnesium. Magnesium is a HCP with A is given to us this much, density is given this much. We are asked to find out the radius of this. By using this relation, one can obtain the radius of the magnesium. So in this way, magnesium radius we obtain by using the formula A is equal to 2R, we will get R 160 p. So question may be asked in examination about the radius of the FCC or volume of the FCC or age of the FCC, depending upon the nature of the question. We have to utilize formula, and by substituting the values in the same unit, if it is nanometer, in SI system you make it, or if all the units are given in CGS, you keep it in CGS, and then substituting the proper values in correct formula, we obtain the required quantity mathematically. Thank you. In next lecture we discuss the remaining matter.